Okay, so to further comments about calibration, I wanted to make some additional remarks. One question that was just brought up by Amir concerned the fact that when we're calibrating, we're making use of data regarding the emergent patterns of the system, regarding the emergent behavior of the system. And the data that we'll use in that is data where the system is predicting values. It's values endogenously produced by the system. It's generating the values. And there's another very important use of such data beyond calibration, to wit, using it for validation or developing confidence in the model. Calibration itself does involve interrogating the model and struggling with it. It involves trying to understand why it's falling short in matching to certain data, and trying to understand where the tensions are in the theory that we've presented in the model. Why it is that it can't simultaneously match, for example, high numbers of individuals who are latently infected and high numbers who are developing active TB or what have you. Why it's off with one while being higher in the other or what have you. There's a certain amount of confidence building that goes on about the model for that. But there's often a separate process that's undertaken, and I'll highlight that in my slides here. A separate process that's undertaken which involves an explicit gating to sort of test the model against data not used in building it. There, in the so-called validation process, we're trying to evaluate whether the model adequately accounts for the patterns that we see. And there's a very important process here in model testing called cross-validation. And this is a process which I use extensively as sort of a routine thing over on another side of my work, namely machine learning and big data analysis, where it's typical to engage in cross-validation. And the idea here with cross-validation is reserving parts of the data to which you have recourse for checking model predictions, for evaluating model predictions, while using only a subset of that data for building the model. So we might use 75% of the model, of the data to build the model, including calibration, and then a remaining 25% for testing. And the most typical way we see this within dynamic modeling is that we basically calibrate the model to a certain point in time. Thanks, Grayson. And then we compare model predictions over later points in time. Okay, so maybe we'll calibrate a model to 2012, and then the last 5 years of data we'll compare model predictions against those data items, running the model forward from 2012. That's the most common way in which you see this used. In some cases, other projects, there's data from certain data sets that's taken aside. So it's not so much a dividing it up in time, or time before a certain point is used for building, calibrating the model. Time after that is used for prediction, but instead subsets of the data sources are taken aside and only used when we are testing the model to predict what those data sources should look like. And we use that as kind of a vetting of the model. These are both techniques that can be readily used with models. In both cases, we're not dealing, typically we don't have the luxury of having data that's somehow independent or uncorrelated, because we're dealing with these systems where it's tangled together causally. One way or the other, if we put aside whole data sets about certain factors, or we put aside data from most recent years, calibrating only up to a certain year and then predicting forward, the data set after that time or in the data sets that have been placed aside in escrow, those are not totally independent of the ones to which we have calibrated. There's some relationship there, typically, statistically. So neither one is a perfect opportunity to test the model, with independent data. But cross-validation is certainly a technique that can raise much greater confidence the model is behaving well. And this most common form of it, where we calibrate till 5 years ago and then predict forward, we will often look to that as a basic evidence that the model is capturing current patterns well before we start looking at counterfactuals. So you'll find a lot of models there in the literature which do that, which perhaps calibrate or parameterize till 5 years back, predict the most recent years to make sure that it's capturing the requisite patterns. And then you ask counterfactuals, with the thought being that the baseline scenario is kind of the current scenario, and then you can ask what if about that. And those ones that are matching the current scenario are, you've demonstrated that the model is able to capture the basic dynamics of the situation currently. So cross-validation here is a technique that requires some planning ahead. It requires some decisions as to what an appropriate year is, and you need to take into account which years is data available. In a fair number of cases that I've seen, we don't have data currently for the last 2 years for one reason or another. So there you might end up going 7 years back. So you have 5 years, where you are predicting forward and 5 years not. Now, in the machine learning context, we often do n-fold cross-validation. And in this context, what we do is we knock out different subsets of data and systematically rotate through in kind of a round-robin fashion, having subset A and predicting subset B, having subset B predicting subset A. And with tenfold cross-validation, we'll do that for 10 different units, each time having 9/10 of the data used for perhaps training, 1/10 for prediction, and we'll systematically evaluate it with that. With dynamic models, the tools aren't there to allow us to do that with facility, and certainly it is not generally possible to calibrate it to later data and have it predict earlier data. That tends not to work all that effectively. Although there are times where if you're just calibrating parameter values, not initial values, that can actually work okay. So cross-validation, I would say, as a technique, it has long been applied in simulation modeling and dynamic simulation as a rigorous, automatic, multifaceted approach. It is not really well supported by existing tool sets in terms of automatically allowing you to kind of take different subsets of data like we do in the machine learning context with pipelines and so on. And I think this is an area of growth. I wouldn't be surprised if in the next 5 years, one of my students or an intellectual progeny of Winchell or something takes this on as a task, builds a toolkit for conducting with any logic formal cross-validation in an automated way, and then we can formally specify, statistics about the performance of the model in the context of cross-validation.
We also see utility of using a system dynamics model to cross-validate an agent-based.
Good question. It's interesting because many times have I used in the same modeling project multiple models. And many times have I noted that I think that using models built separately, not one depending on the output of the other or what have you, that those models can offer a lot of cross-checking of each other's findings and can sharpen at the least one's thinking, and can often help yield confidence, conviction even sometimes, that what's been captured in terms of model expectations is solid. I think system dynamics and agent-based modeling, is one way to do it, or different methodologies. And there, you're unlikely to make the same mistakes in one that you are in the other. There's enough difference in the traditions that you're unlikely to just fall into the same traps for certain types of issues. Certainly, you're unlikely to have the same bugs, in the model. You may have the same systematic misinterpretation. I'll give an example. So we've worked a lot with our provincial TB control program, and with some of the most senior figures in that area who led that program for many years, but have now moved on. And there, in the models that we build, we may bring certain assumptions to the table, such as the fact that there's very low likelihood of reinfection given latent TB infection. If you're already infected, you're unlikely to get infected again. And that's a contentious thing in the literature. There are some people who believe you are open to getting infected by a different strain or what have you. And I think one would want to go beyond just having two models, each built with similar assumptions, to models built with alternative assumptions also about this, which really gets into sensitivity analysis and gets into interactions of calibration and sensitivity analysis. Now, one of my students, very strong student, Yuen Tian, who's working for our Ministry of Health to lead the modeling there, she's done some very interesting work, and I'm a little bit associated with it. I was involved in it to a degree, with an approach called GLEW, G-L-E-W, which basically combines together calibration and sensitivity. This is a very important point because, often what's most commonly done in simulation is that people calibrate the model and then they conduct sensitivity, or you conduct sensitivity analysis to identify the parameters most worth calibrating, and then you calibrate them and you're done. But what this methodology was highlighting, this GLEW methodology, and we have a paper about it if people are interested, was highlighting the fact that if you do sensitivity analysis, it's a little bit, how shall I say it? Stretching it. To say, okay, we'll do a sensitivity analysis, find those parameters to calibrate, and then we'll calibrate those. Because if you do a sensitivity analysis, sometimes what you find is that from the result of the sensitivity analysis, you see things which are very unlike the empirical data. And there might be a consistent theory there with this alternative value of the parameter, but it would involve recalibrating the model so that other parameters were made consistent with it. So what I'm trying to say is, when you're calibrating, you're trying to find a consistent hypothesis for a bunch of different parameters often that best explain the observed data. And if you vary each one in isolation, you may get something that's very different than the observed values. And we might, at the same time, be able to consider an alternative value of this parameter, a value which assumes this value, but we need to adjust the other parameters with it. So, we could either have rate of transmission high and rate of reactivation low, or vice versa. But you can't have one in isolation and of the other. And there are times where you want to vary a parameter and then do a recalibration with that alternative value of the parameter to find sort of what that consistent hypothesis would look like. If you posited that we have no reinfection going on, what would that imply about all the other parameter values in the model? And then we want to say, okay, if we did have reinfection going on, what would that imply? And you calibrate to that. So in GLUE, UN applied that approach, but she did more than that. And this is, I think, one of the areas that got really interesting. And I got to credit my colleague Kristen Hess-Miller-Lich for her sort of persistent interest in this. What UN further did was to look at how sensitive are not just the model outputs with respect to these criteria, how sensitive is the ordering between interventions? Like when you change these assumptions, okay, maybe it changes model output. We change assumption, this parameter value, and it changes how the model outputs in a big way. But maybe despite that change, with the original value of the parameter A, intervention A looks much better than intervention B. With that parameter change, also A looks much better than B. It didn't really change the ordering. It didn't really change what we care about. Sure, it changed the model, behavior, but maybe for both A and B, it just, led to more, comparably more higher output in both cases. So it didn't really change the ordering. And so she was looking at, to what degree in the stroke model, it was a system-dynamic stroke model, the results would be different if you were to have these alternative parameter values. And she was looking to what degree is there a flipping of, between the most desirable interventions or what have you. It's an interesting piece, and it brings home the fact that sometimes we perform calibration and sensitivity together, and sometimes we perform sensitivity with respect to intervention selection, intervention desirability, not just with respect to model output. Yeah. Long answer to a short question. No. Other questions? So, I'll tell you this. Calibration is not easy. Calibration is not easy. It happens to be one of these areas where I specialized in it. And in some ways, it reminds me a lot of debugging, to be honest. A lot of the process of debugging programs. Really, you're trying to burrow down to figure out why we see these patterns. Why is it that we can't match this? And it requires a lot of ingenuity to try to tease out that why. And often here, we are, okay, here's various things in any logic for this. You'll find lots of pieces here. There's some guidance on calibration. One of the best things I'd like to suggest to students, if they're having problems calibrating the model, say that's really a poor calibration. Okay, that's a good starting point. So now we have to ask why. In order to get a sense of why, one way to do it is to basically try to outsmart the calibration. Say, okay, I bet I can do better than this. Let me manually tweak these parameter values, right? Try to adjust them so I can do better. And as you're adjusting them, you'll start to notice things about the results that are different. Maybe you'll notice the objective getting worse. And you've got to understand, why is it getting worse? Maybe it's improving its match to these time points or this data, but it's worsening its match with respect to the other. And you've got to figure out, what is that telling you about the fundamental tensions here about your hypothesis? Why is it that, if you match number of reactivated TB cases or number of TB cases of recent years, you can't match deaths? What is it about this data that is about the model that's causing it to be unable to match both at once? Now, if you can match both at once, if you can do better at the calibration, then that's a sign that it's not exploring the space well. There's something else going on there. But typically what happens is you discover a bug in your thinking. You realize, oh yeah, that can't be high without this being low, without that being low, and therefore without this other thing being low. Okay, now I understand, why it's having trouble, because in our model, basically we can't really have those two things be high and still be consistent with the data. And that gets you thinking about what is it about your thinking that's going on? Is it possible that you've been ignoring differential diagnosis rates? Or is it possible you've been ignoring two types of active TB, one infectious, one non-infectious, one unreported, one that is reported? So that's an important criteria. Another thing is that, sort of along the same lines, you're trying to match two things, and let's go take a look at our model here. Trying to match two different items here. Maybe we want to weight one different than the other. We'll have 0.9 times this, and 0.1 times this. Right? Here it's going to give preference to matching this. And then the question is, okay, is this mismatch going to get really bad? What if it tries to put all its emphasis or most of its emphasis on this? Is that going to lead the balloon to pop out somewhere else? Squeeze it here, it pops out over there, right? These are how you learn about why it's having a tough time. And again, this is not a nuisance. This is not just lost time. This is a lot of the learning here, because you carry away a feel from the model. Now, that's something that's really emphasized in system dynamics. It's not so emphasized in the agent-based modeling literature, which is more kind of, you let the model tell you. But I think it's really valuable to have a feel for how the model is interpreting things, or when it's simulating the data, what is it that it has to struggle with in calibration to match both. So struggling with calibration is worth it. And I have a long history of doing that. And one point of wisdom is it takes a while, and it takes a while in general, and it takes even longer with agent-based models. Why would it take longer with agent-based models?
More parameters, more variables?
Okay, sometimes there's more parameters. Generally speaking, this is an identifiability issue for those who are familiar with statistics. If you're trying to calibrate 100 parameters and all you've got is a few pieces of data, you're on a fool's errand. I mean, you're going to overfit it. There's going to be many different interpretations to this thing, and you're going to end up in one arbitrary one, and it's going to be very specific to those data points, and your model might not have a lot of generality coming out of that. So you need an amount of data that you're matching in calibration that is, is enough to tie down the parameters. And sometimes with an agent-based model, you have more parameters that are less well known because you have more articulated representation of causal pathways. Ladies and gentlemen, in aggregate models, which often happen to be in system dynamics, but it's nothing about system dynamics inherently. System dynamics can be at an agent level, and I think is often best suited to that. When you're dealing with aggregate level models, it's hard to have an articulated representation of causal pathways. It's really hard to have a very detailed representation of the causal pathways because often they depend on individual circumstance and heterogeneity and so on. It's hard to have a really nice representation. So an agent-based model often will have more parameters, and it takes longer. You're exploring a bigger space. Even if you have enough evidence to be used, it's exploring a bigger space. But what's another reason that takes longer in agent-based models? Besides the larger number of parameters. It's slower to run. There's a lot more moving parts in the model. And simulating an aggregate model of a system might take a second. Sometimes less. It's sometimes whip fast. It just immediately simulated. In a corresponding agent-based model, minutes, hours, better part of a day sometimes. For large models, I mean, hundreds of thousands of people, wait till you see wind chills. Don't say I didn't warn. So a month. So, ladies and gentlemen, month seems to me excessive, but at the least we're talking many minutes. At least we're talking many minutes. Yeah, you hope after a month you didn't, use the wrong parameter value. Yeah, no, this is a real issue if you have long time. But more to the point, it gets in the way of quick iteration. And this is one of the reasons I think that one is advised to often start with a much coarser model because you can iterate towards learning with it much sooner while you're trying to build up another model. Now, agent-based models can be simple. They can be limited in boundary, and they will run somewhat faster. But even there, you get hit by the combinatorics once you go to 100,000 people or 400,000 people. It will take some time. Moreover, and maybe this is part of the calculus of a month, I trust that it is, you need to run multiple realizations. And so there, presumably, you're running on 3 machines, partly to capture the different realizations, to get some degree of variability between the outputs. And so calibration is a great opportunity to learn, but it requires patience, it requires careful experimentation, it requires really grappling with thinking, kind of putting yourself into the standpoint of the model. Putting yourself, think about this theory the model's capturing. What is it that's giving it trouble? And often that involves looking at intermediate variables, trying to understand why it's matching this one well, but not that. What is it thinking? When it's matching this one, what is it thinking in terms of the latent variables is going on? And that will help you understand why it's not matching these other two things. So you end up trying to get into the headspace of the model in terms of the latent variables as well, to sort of understand its perspective on the world, and to understand if it has multiple matches that it can make against the data, what those different hypotheses are. Because often we'll find more than one match that seems to accord for the data. You could have A low and B high, or A high and B low, or anything in between. Sometimes mapping out the space, what's the objective like as you change A and change B, can highlight valleys where you can have very good objective functions for wide ranges of both A and B if they covary together. So there's a lot of investigation that are needed here, but it's not time wasted. It's not just we got to get beyond this so we can give policy recommendations. This is actually often what is used to get the learning that goes into those recommendations. It gives an idea for scenarios, etc. And I will say, you got to. There's some amount of training to do this well, and it takes a certain doggedness, stick-to-itiveness to kind of go with this and tussle with it, to find out things. You can set some weights to 0 to see, okay, if I only try to match these two things, now what does it think about the latent factors? Now what does it think is going on? What is it thinking? That's what often I come to with these models. What is it thinking? What in the world is it thinking? And it's quite nice to have recourse to a number of machines for this. If you could if it runs for a month, then what you want to do is you want to run several different scenarios, get them going in a staggered way. So every few days or every week you could have new results to look at, and you want to have good reporting for what's going on inside that model, so that you don't go for the month to say, oh, that's weird, wonder what it's thinking. Let's add a couple of reporting of these latent factors. Now let's start it running again, and we'll go back and access it when the snow melts or something like that. Sorry, you don't have snow here, I guess. There's a snowy river though, right? Yeah. So here you're fighting with things. A couple things that are really good experiments. Increased parameter range. You're going to be looking, okay, is it getting to best parameter values that are at the edge of its range? If we allow parameters to only vary over certain ranges, or what it's getting for the calibration only applicable at the end of the range. Let's look for parameters here. Check it out. Here I have a slide on this that I should have emphasized. It's back here, just a little bit. Forgive me for going back. There's a thing here. A lot of this is explaining any logic components. Okay, and here we go. Required information. What are you trying to match? And the objective function you want to use. What parameters you want to vary, over what range to vary them, and then the optimization algorithm. For any logic, the optimization algorithm is largely given. But what parameters what data you want to match is here, and then what parameters you're going to be vary, and over what range you're varying them. So here it's saying we could do it from 3 to 30. If this came back with an indication that the best value for a contact rate was 0.5, let's say, really? That suggests that it may well get even better if it's lower than 0.5. And we've kind of interrupted it artificially. And we need to think about, okay, to what degree do we want to open that possibility up, that it's less than that? Or is that so outside the bounds of what seems plausible that it suggests that the model's theory of things is questionable? And a lot of what we'll be trying to explore is, well, okay, again, what is it thinking? What does it think is going on with these latent factors that I'm not observing that makes it want to have this be smaller? Why does it feel that that's even better to go down there? So a little bit more on calibration here, and I'm going to have to, again, skip around here. Another thing that you'll want to sometimes do is say, okay, if I modified the model in this certain way. I remember one TB model many years ago. I remember I was running this over Christmas vacation. Kind of go up and have some pie or something, and then I'd come downstairs and check what the simulation has brought in. It was really good. It was maybe better what's under the Christmas tree. It was really great. There was a lot of learning going on, but it took iteration, and this was even with that particular one was with a system dynamics model. So increasing number of parameters. Go down this route cautiously, adding dimensionality. Ladies and gentlemen, to search in one dimension, it's like searching along here. It can be expensive, but you're trying to find the best value somewhere in here. Searching in 2 dimensions is like searching, on this. Now you got to kind of wander around and try to find it. Searching at 3 dimensions, it's like searching inside of this cup. You got to go up, up this way and this way. And you got to search around. 4 dimensions. Well, I won't ask you to imagine it, but it's like you have an additional element of time associated with it. You got to find at what point there was this thing in this cup or something like that. At what time it was in there, and you got to search over the entire time of the boot camp. For some, perhaps it'll be traumatic. Increasing number of parameters. It raises the risk of overfitting. You've got too many things you're trying to vary, and of course you're going to be able to match. There might not be one match, many matches, and it might not be very, very general. So changing model structure often gives a lot of insights. So if we were to change this model structure, so we changed it so we have uninfectious active TB and infectious active TB, how much does that, even with rough representation of the time constants between them, how much does that really change the results? Does that make it a lot easier for it to account for these things? These are things that we'll often do. And you could run, large number of these runs at once with these different components. This is one of the things we do with clients, because we do have access to hundreds of machines, and we have maestros like Winchell who could just do conduct orchestration of all these different runs over these machines. Student labs, while the students sleep, the machines do not. They can be running large numbers of things for our partners. And the harvest in Saskatchewan is rich in both fields and in the labs. We can run it for a larger number of optimization runs to explore the space more completely. Or we could try to remove sometimes parameters from there by finding additional values. Calibration is a labor of love, and you need to approach it as a learning opportunity, and you need to apply yourself to it, run things in parallel as much as possible, really be creative, talk to someone who spent a lot of time calibrating, and try to record what's going on a lot of different factors so you don't have to rerun runs, and try to keep a good lab notebook so that you have a record of what you've learned. So you don't have to revisit the same thing again because you didn't record what the findings were. The good news is with AnyLogic 8 and with cloud-based computation, this may get easier. We can run more things in parallel, but we can't necessarily run them faster, that much faster. So maybe the month-long model can be done in 20 days on Amazon Cloud. But more to the point, it can be done with many different parameter values at once, or with many different model variants at once. So that's a lot of the benefit. So you're going to be wanting to explore our calibration values unique. If they're not, or if there are many possible values that suggested, if we run this thing many times, we get different parameter values suggested for our run back here. If we run this many times, we get different ones. What's going on? Do those give basically the same interpretation? Do they give the same intervention trade-offs for each of those possible interpretations? These are important questions. So these are things that you're going to want to look at in the context of calibration. Okay, and again, I don't know why this is toning out here. Let's see, one or two other comments on calibration. Calibration is a approach that is fairly heavyweight. I might conduct it on an occasional basis with a model. After lunch, we'll be looking at a sort of approach to calibration that involves constantly keeping a model in tune with the latest data. So rather than having a big effort to calibrate and then enjoying the fruits of our labor subsequently, we end up doing calibration every time a new data point comes in automatically. And the technique there is particle filtering. And we'll be exploring that after lunch. Okay, so here, calibration, we have a model. We are trying to get the model to match observable data that relates not to one parameter, but to a model output that is probably yields many entangled values. We are systematically varying parameter values and trying to match it. There's a related technique. So one thing that comes out of calibration is one best estimate for parameters typically. And as an alternative to that, we've explored strategies and been quite successful in use of them with a number of models, which have basically sought to use Bayesian techniques. And one form of that is particle filtering, but another form is what's called Markov chain Monte Carlo methods. And with Markov chain Monte Carlo methods, basically what you're doing is, instead of trying to find the single best set of parameter values, what you're doing instead is seeking to assess a probability distribution, a so-called posterior distribution over parameter values, where some of them match the data better than others. So you're not trying to find the single best match in discarding the others. Rather, you try to arrive at a probability distribution over those parameter values, recognizing that the data itself is noisy, that there may be different matches that are all somewhat plausible, but some are better than others. And so we make use of a prior distribution over parameters, which sort of reflects our best guesses up front without having seen the data. And then we have beyond a prior distribution, we have a likelihood function, which basically specifies, given these parameters and the model output that comes from them, what is the likelihood of observing the observed data that we have in hand? And then we use this Markov chain Monte Carlo algorithm, which basically samples from this distribution. It draws values from this distribution of parameter values, with more plausible parameter values being drawn more commonly. And so that gives us the ability to sample from a distribution of plausible parameter values. What we do then, having done that, the beautiful thing is this is better than arriving at confidence limits or something in a frequentist context, because then we can actually run forward the simulation with different interventions and get posterior distributions over intervention gains from baseline, or posterior distributions over an intervention's cost effectiveness, or posterior distributions over an intervention's number of cases averted, or what have you. And that's very powerful, particularly when you can say, okay, this intervention, with 90% of the cases, this intervention is better than that one. So in other words, given the uncertainty about the parameter values, we can still recommend this intervention more than this other one. So that kind of combines elements of sensitivity analysis and calibration together.
Could you also sample over different models as well?
Yes. Yeah, you can. It's more involved. There's a
Reversible jump.
precisely. Man, you're great. It's reversible jump Markov chain Monte Carlo techniques. You can do it. The challenge here, which I think you're sort of getting into, is that if you're dealing with models that have the same parameters exactly, this is less hard, because you're exploring a space of parameter values. You're sampling from parameter values, and here for model A and model B, they're both operating with the same parameters, and so we can assess their goodness of it. It's not the goodness, the likelihood is a function not just of the parameter values used, but which model is used. But when we're dealing with models which have different numbers of parameters, maybe one has two states that are collapsed into one in a state chart, and we run that, then we are getting at challenges which involve exploring a parameter space which is different between the two models. And reversible jump Markov chain Monte Carlo techniques are a way of dealing with this fact. Now, that's an advanced topic within Markov chain Monte Carlo tools. It's a fairly more, in contrast to MCMC, which has been around since Metropolis and the 1940s. It was first used sadly enough, in the Manhattan Project. These days, those techniques are quite well established MCMC techniques. Reversible jump techniques are much more recent and involve more sophistication. What a bigger challenge is that for MCMC, I'm told by my mathematical statistician colleagues that really one should be performing MCMC with models that are deterministic, not models that are stochastic. And if you're trying to use models that are stochastic, particle filtering you're going to be wanting to think about, not MCMC. So for most agent-based models, not all, but most agent-based are stochastic, and MCMC might not be a good fit in that context. System dynamics models, it can be a good fit. Aggregate system dynamics models, I should say. Okay. Anyway, those are some comments on, further comments on calibration. Any questions? Further questions before we finish up with that? I appreciate your patience with this. Here we go.